Okay. So if you have any question, you just type in the chat box, and then I will read it and give you any reply. Even say, okay, but I couldn't understand this part, I may explain more. Okay, so let's record first. What happened to my pen? Okay, record what we studied last week. So we introduced the function of two variables, right? And then we talk about the limit, right, at a specific point. And then we talk about the continuity. So when we are talking about the continuity, first you have to have the limit, and the limit equals to the value, and then we say the function is continuous at a specific point. After that, we talk about the partial derivative, right? For the partial derivative, we first have the first partial derivative fx, fy, and then we introduce this f or write this. This is d, this is nabula. Anyway, s is fx, this is fy. It has a lamp for the gradient, right? And then we continue to compute the second derivative fx, fxy, fy, fyy. We write this as a Hessian. So this is called the Hessian of f, right? Gradient of f, just a name. And also there is a theorem. The theorem says if we have a function f and fx, fy are continuous, then fxy is fyx. Right, this is the theorem. You have to know all of this. Anyway, so let's erase some extra one. So today we are going to talk about 14.4. It's about the tangent, planes, and linear approximation. So let's stop check if I make a record. Okay, yes. So let's first talk about the tangent plane. Like we said, if we have function f from a subset in R2 to R, we can consider the graph of f, which is x, y, and fxy, xy is in D. So we can graph it. So in this way, so this is okay. X, Y, Z. So this is fxy. This is D. This is D in R2, right? So this is the graph of f in R3 in 3D. Okay. Oh, explain. For any point A, B, right, in D, we can find the value this. So let me change the color. So this is F, A, B, right? And then we can find many curves in the graph or on the graph. This is curve 1. We can say this is gamma 1. Okay. And then we can have another curve, gamma 2. But we know for any curve, we can compute its tangent line, right? For gamma 1, we have the tangent line at this point. And also for gamma 2, we have another tangent line. Okay, we have 2 lines, right? For these 2 lines, we have, we can say this is L1, this is L2, right? And then L2 and L1 and L2, if you look at the picture, can spline a plane, right? So you don't have to understand my language like this, but you have to know what I'm drawing. You may ask what I'm spline. Spline just a linear algebra notation, but you know what I'm doing, right? Just it's spline a plane, right? You know, if you look at the picture, my plane is kind of parallelogram, right? But you know, you can draw more, right? We used this idea before, right? We have a plane. Okay, this plane is called the tangent plane at the point A, B, F, A, B. So now, up to now, I introduced the tangent plane. Okay. Okay. Now our question is find the equation of the tangent plane at the point A, B, F, A, B. Okay, that's our question, bro. So there are many ways to understand this. So you may say tangent plane is a plane. If you want to know the tangent plane, you have to know one point and also find the normal vector field, right? Yes, that's right. So, but let's first, we will not require you to do the proof. Let's first tell you how to write out the tangent plane, and then I'll explain you why this is the tangent plane. So this is the theorem. So let f from D to R is a function of 2 variables. A, B is a point in D. So the equation of the tangent plane, the equation of tangent plane at A, B, F, A, B is, or I hope you can say, is Z minus F, A, B equals to F, X. Here, be careful. This is a partial derivative. You evaluate at A, B, you get a number. Multiply, this is the number, multiplied by X minus A plus F, Y, the partial derivative of F, evaluate at A, B. I will emphasize this because by my experience, always some students get this part is a function of X. No, it's a number. Okay. No matter how many times I emphasize, always there is a student made a mistake like this. I just couldn't understand this, right? Maybe they just don't listen to me here. Anyway, this is a number. This is a number. This is not a function of X and Y, because after you compute fx, you evaluate at this point you are considering. So means that this is a number. Okay. So this is the equation of the tangent plane at the point of AB, FAB. Okay. So let me explain why it's This is right. Okay, someone is talking. Can I email the file? Okay, you can email it to me now. Oh, okay. So let's go to second page. Explain it a little bit. So let me explain it for you. So we say if we have this is the surface where the graph of f. So like here, what we said, we have two curve. Here, we will introduce two special curve to help you to understand it. So we have a 3D, right? This is AB. This is F, AB. And then we consider the, we fix Y, X is changing, right? And then for this segment, its math is X curve, right? And then if we fix the Y or fix the X, we get another segment. Let me change the color. Right? So the map is another curve. We call it a Y curve. Right? And then we can write the graph in this form: X, Y, F, X, Y. So let me first talk about we fixed Y. After fixed Y, we get a curve. We write it as Rx because Y is fixed. Okay, this is X, Y, but you have to write Y. You cannot say I don't write Y because we are doing problem in R3. If you didn't write Y, R2, that's not what we are talking about. Okay, F, X, Y, and then we compute the derivative. We know the derivative is the tangent, we know the derivative is the tangent line, right? So we get 1, 0, fx, right? So it's kind of, this is the, okay, let me change the color. So this is the vector. This is the tangent line. Its vector, direction vector is 0, 1, fx. Okay. And then, so let me change it back to red. We fix the x. We have y. Our y is x, y, f, x, y. And then we compute the derivative. This is 0, 1, f, y. So, and then we know if y is changing for this curve. If you compute the derivative, you get the tangent line, right? This is the direction vector of the tangent line for y curve. This is 0, 1, f, y, right? Like what I said before, there's two tangent line span a plane, right? It's kind of, now we have a plane which is passing through the point A, B, F, A, B, and we have two vectors into plane, and then we can compute the n. N is, we can write this is V1, this is V2, this is V1 cross product V2, and then we try to compute it. Okay, but here you have to evaluate this at AB, Okay, so let me compute it. So we have I, J, K. Okay, there 1, 0 fx, 0 1 fy. We compute this, you will get this is negative fx. Look at this. If you look at this, what's this? This fy. So, okay, this is 1. So we got the normal vector. You have to remember this at every point. Fx, Fy is 1. But here, because we are talking about a specific point A, B, in fact, you can do this process at every point. But here we only care about 1 point. That's why we get A, B, its value. Okay, this is a normal vector. By what we knew before, if we know this, we can directly write, because this is a vector field, the normal vector, we can fx evaluate at a, b, and x minus a minus fy a, b, y minus b, plus the third component is 1, and z minus f a, b is equal to 0. That's why finally z minus f a, b, it's a value, it's a number. Okay, fx, it's a number, x minus a plus fy evaluated at a, b, multiplied by y, multiplied by b. That's the equation. You may say you don't understand, you don't want to understand what I'm talking about, but you have to know this. You don't have to understand this part if you think it's hard, but if you can understand, okay, that's good, right? You have more understanding, it helps you to understand the other stuff. But you have to memorize this for function. Okay, how do we, the equation of the tangent plane at the point of AB, FAB is this. It's very important. So this is a formula. Very important, okay. So let us look at examples. So change the color by example. So the first example is find the tangent plane to the function 2x squared plus y squared at the point of 1, 1, 3. Find the tangent plane to the function z 2x squared plus y squared at this point by the formula, right? So first, if you look at this, you have to compute fx at 1, 1, fy at 1, 1, and fab. This problem already told you ab is 3, right? So let's first compute fx. Fx is just 4x, right? Fy is just 2y. So fx11 is 4 because the x is 1. Fy11 is 2, right? So by the formula, we have z minus 3 equals to 4x minus 1. Like what I said, this is a number, okay? Plus 2. Or maybe you can argue with me, you know, everything is a number, right? In math, right? X is a number. I say it's a constant. It is independent of x and y and z, right? Okay, y minus 1. So you can simplify it. In general, we write it in this form: 2x plus 2y minus z minus 4 minus x plus minus 8 plus 5. I think, oh, I'm wrong. So minus 4, 6, okay, plus 3. So let's write a remark. In general, you have to write your plane, the equation of the plane in this form. Okay, it's kind of part of the requirement of our class. Okay, this is D, not a bracket. Okay, A, B, C, you write it this form. So this is the tangent plane, the equation of the tangent plane. you may find more examples and try to figure out. Okay, if you knew what I do, this example is enough because every problem is just follow the same procedure, the process, and get the final answer. So you may ask me, why do you talk about this? You know, why we talk about the tangent plane, or why did we talk about the tangent line before? Okay, if you ask this kind of question, that's a good question. You know, we understand, you know, we have some strategies, you know, okay, strategy to understand the irregular object, you know. So what do you mean the irregular? So first I have to tell you what's the regular object. Oh, what you studied in your elementary school, middle school, that is regular, like the line, points, tangent, no, plane, rectangular, parallelogram, cubes. That kind of object is regular because the shape is good. But in college, we are focused on something that's not irregular. Okay, how do you understand it? Oh, we always use the regular object to approximate the irregular object. Okay, and that's why we introduce the tangent plane, because the tangent plane is regular one. The general surface is regular or is irregular. Okay, we want to approximate it, right? If you study the economy, or I think only in pure math we talk about some very imaginary. If you study other field like even food science, economy, engineering, like that, you only care about something regular. If it's irregular, you can only handle the regular one, use the regular one to approximate the irregular one. Okay. So with, you know, like what I said, let's continue to use the idea, use the regular one to approximate the irregular one. So, and then let's talk about the linear approximation. Okay. So like we have a surface or a graph of function. Like what I said before, sometimes I say a surface, sometimes I say a graph. They're the same because we made this convention before in our class. Okay, this is a graph of F, or I call it the surface. Right. So we have a point. In general, the surface may probably is very bad. You know, we don't know how complicated the surface could be. Okay, but we know the information at this point, and then we have the tangent plane. Now, wait, what happened? So we have a tangent plane at this point. This is the tangent plane, right? We only know the information at this point and know how, you know, we only know information at this point. We don't know the information. We don't know too much information about the surface, but we still want to understand the surface. How do we understand it? There is a rule. There is a method. It's called the linear approximation. Like what we did, we defined. So we defined L, X, Y, as we know at the point A, B, we have F, A, B, right? This is the point. Okay, we know this, and then we want to know around this point, what will happen, right? So we have F, X at A, B, and X minus A plus F, Y, A, B, and X or Y minus B. So this is defined as the linear approximation of f at the point of AB, right? So let me think in another way, because if I draw a picture like that, you may say it's hard to understand it. So let me draw a better picture to help you to understand it. So, okay, so now our function is like this. Okay, this is kind of a problem, right? So if you look at this point, right, we have a tangent plane. Right? This is our tangent plane. At this point, now you can think the parabola is above the plane, because for myself it's easier to understand it. So now we define L x y is f a b plus f x a b plus x minus a plus f y evaluated at a b y minus b. Okay, this is a linear function, right? And then we have a real value, the real value is fxy. The problem is that we don't know this. Our goal is that, okay, we know information at this point, you can write out the linear approximation and then try to understand this value and try to use this, replace this, or approximate this. You can say FAB is LAB. At this point, AB, they are the same. But when X, Y are away from A and B, the point of AB, we don't know what's the relationship AB, but we still, in general, if F is not that bad, okay, this can approximate F, and LXY can approximate FXY. So you may say, why do you do that? So the problem is that, okay, let me show you an example, and let me say, okay, why, how do we, do the process what I'm talking about? So how do we apply it? Okay, first we can write a remark before I go into the examples. We can always use X, Y. We can replace Fxy by Lxy, right? So it's kind of, you can see Fxy in Lxy. So if you study some subject, you feel that, especially in economy, right? The data is always rough data, right? You don't know the actual information. You just use the rough data or the data you collect to try to mimic the real world or what happened in real world. Okay. So let's continue talk about this. After we have the linear approximation, you can, okay, let's continue to write a remark. You may ask me, what's the relationship between the linear approximation and the tangent plane? You can say Lxy is FAB plus FXAB x minus A plus FY evaluated AB y minus B. This is linear approximation. Okay. And then we have Z is FAB plus FXAB x minus A plus FYAB y minus B. You can say the only difference tangent. Nay. equation. What equation with the tangent plane? Okay. You can say only difference is here. Right. In fact, they're same, but if there is a problem is asking you write the tangent plane, you cannot write the linear approximation because they are different. Okay. So after we know the tangent plane, so okay. We have this motivation. So we have L x y is FAB plus FXAB x minus A plus FYAB and Y minus B. But like what I said, this, if you look at the remark, we say LXY is almost XY, not for any X, as XY is close to AB. For example, you may say, why? You know, like what happens if XY is very, very far from AB? Nobody knows what will happen. We can only know the information close to AB. Okay. So we can approximate, assume, because this is almost fxy, almost, I didn't say they are equal, right? We can write this xy, and this is almost AB plus fx, AB, x minus A plus fy, A evaluate AB, y minus B, almost as xy is close to AB, right? That's right. And then, but we know as xy approach to AB, you know, FAB is LAB, right? They're just the same, right? And then we can just assume we net x, y. No, let me write it separately. So let x approach to A, y approaches to B, and then we can say when x approaches to A, B, x approaches to A, y approaches to B, we can say they are the same, and then let's continue to change the x, y minus FAB is FX AB x minus A plus FY AB YB. I only change one place, you know. Just move the FAB from the right hand side to the left hand side. That's what I did. Okay. So what says by our previous notation, right? This is delta. If we write Z is FXY, this is delta Z or just delta F, right? This is the notation what we know before. This is the difference of 2 points. We write it as a delta Z or delta F. This is just a definition. Okay, and then this is, if you didn't count the errors, you can write this as fx AB. You write this is delta x, right? Delta x is just a definition. We know this, right? Fy evaluate A, B, and y minus B. Oh, sorry, I forgot to change it. This is delta y. Okay, this is as delta x, delta y approach to 0, 0. This is equivalent to x approach to A, y approach to B, right? This is equivalent to delta x approach to 0, delta y approach to 0. Nothing new, right? Just, you know, use different notation too, right? So the whole process is just, you know, format. It's not the proof. I just say what we did. Let me know what I'm doing. And after I introduce this, I can introduce the differential of a function at AB, so which is delta Z or delta F. Okay, at AB, or you can say at AB is defined at Fx AB delta X plus Fy AB delta Y plus some error like this, delta X plus delta Y. So if you look at what I said, what I wrote before, I always say almost, right? But here I use equal. When I was using the equal, I mean that, you know, as X approaches to 0, you know, here the differential is this with this plus the extra term. This is kind of the, you know, said, tells us this is the first order, this is the first order. The second order is small. Means that as X approaches to AB, if you ignore the second order, okay, this is equal to this, because this is the linear approximation, right? So means that the linear approximation can almost approximate the original function. So you may ask me, okay, how do we know a function can be, how do I know if a function can be written as this form? That's very hard. But for you guys, I will tell you a theorem. You just say, okay, if this function has some properties, and the function can always write in this format. Okay. So let me tell you a theorem. The theorem says, okay, if we have FD from R, and the first one, Fx, Fy exist around AB. Second one, Fx, Fy are continuous. Okay. On D, the third one, no third one. Then F is differentiable. Okay. Maybe I have to change a little bit the differential. So what I can say, I think I made a mistake here. Sorry. Oh, sorry. I have to change it. My sentence is wrong. We call F differentiable at AB if F satisfies with this. In delta F can be written as in this form, means that the second order can be written as in this format. So the problem is that, so you may ask me, when is the function differentiable? This theorem tells us if the partial derivative exists and they are continuous and the function f is differentiable. Okay, in this case, if a function is differentiable, we always write df is fx dx plus fy dy. This is what we know before, right? If we recall df for function of one variable, this is just the fx dx, right? We just do the same process, but here because we have two variables, right? You have to have dx and dy. After this, if we have function f, y, z, automatically you can have df, fx dx plus fy dy plus fz dz. So this is called the differential of a function. So you don't have to care about this part, but you have to know how to compute the differential. That's the important part. Like what I said, I didn't give you a very specific notation and proof about the differential, because for you guys it's unrealistic to tell you that. Otherwise, you will think you cannot understand me. But for math department in general, we will spend a lot of time to try to understand how do we finally prove a function can be written as in this form. Okay. So let us give you examples. So first, we have a function fy is x e x y, right? Right. So the first step, the first one is write out the differential of f at 0, 1. So we know the difference. This is the differential fx 0, 1 dx plus f1 0, 1 dy. Right? If you want to know this, so first you have to compute the fx. So fx is okay, exy plus xy exy. Get them right? Okay. And fy is x squared exy fx 0, 1. Okay, at 0, 1. At 0, 1, if you plug in this number, this is 1, right? F y 0, 1 is 1. So df at the point 0, 1 is dx plus dy, right? So you may ask me, okay, how do now I'm asking to write out the differential at the point, but I didn't tell you if the function is differentiable. Maybe I can just check the theorem, check the theorem for this problem. You can say first fx is exy 1 plus xy, fy is x squared exy, exists and continuous, right? We know f is differentiable on D, and then after we know this, we can compute this, no problem, right? Okay. And then the second one, for the second one is find the linear approximation of f at 0, 1. This is just this FAB plus FXAB x minus a plus FYAB y minus b. You plug in a, b is 0, 1. So here x, y is FAB. What's FAB? Right? FAB is 1. We plus this is 1 x minus a plus 1 multiplied by y minus b, right? So L x y is now a is 1, right? B is 0. We get x plus y, right? So we get the linear approximation is this. So for this specific example, okay, let me analyze it. Now we have fxy is x e x y, right? We have a linear approximation. Okay, this is x plus y. First, you can say this is automatically. First, we can say f this is this. They are both 1. Of course, there should be no problem. If there's a problem, it means that if there is a problem, it means that I made a mistake. Okay. So, and then let me go more. You can imagine. Okay, if you use a calculator, for example, let me check one point. Around this point, we assume x is 1, 0, 0, 0, 1, right? Y is 0, 0, 1. You can say f 1, 0, 0, 1, 0, 0, 1 is 1, 0, 0, 0, 1 e x 1, 0, 0, 0, 1 multiplied by 0, 0, 0, 0, 1. And also you compute the error 0, 1, 1, 1, 1, 0, 0.11, and you plug in them together, you get 0, 1, 1, 1, 1 plus 0, 0, 1. You add them together, you just get a 0, 1, 0, 1, then 0. This is the value from the linear approximation. But you can say this is, if you use a calculator, you can imagine both are close. By my hand, I don't know this. From this, you can know if you compute this, you don't know how big is this one. But if you look at the linear approximation, oh, magically, it's very easy to get a number. But they are close. You just use your calculator to check it by yourself. It's kind of the theoretical theorem tells us, okay, if you don't care about too much about the accuracy, you only want to know around the number around the actual number. The linear approximation is enough. Okay, I just use this example to help you to understand why we study the linear approximation. It's powerful. Okay, in some case. Okay, and then this is a remark, not a part of the problems. Okay. And then let's look at more about the problem. So, okay, approximate f 1.1 negative 1. Approximate mean it doesn't mean you plug in this and use your calculator. Approximate means that you use the linear approximation x, y, plug in this 1 to 1 plus this one, right? You get a 1. So it's kind of around the point 1 and 0. This value is around 1. Specifically, you can understand it for this if x is kind of around 1 and this is around 1, because x is around 1, y is around 1, this is kind of small, and finally they are around 1. Okay, so you can, if you use a calculator, we know by calculator, we know f 1.1 negative 1 is dot 9 this 42. This is the approximate number. This is the accurate number. They are close, right? Still, there are some errors, right? It should be some errors, right? So anyway, from this example, we can see, right? For some example, you can use the linear approximation to understand the real value for this function. Okay. So let us go more. So that's fine. So one more about the differential. One more example about the differential. So you just you just don't have to care about when a function has a differentiable. You just focus on how do we compute the differential for a function. Okay, so if we have a function f(x,y) is a function, sorry. The differential is df at any point. This is, you compute the derivative. This is a function. I emphasize it's a function of xy, and dx plus fy xy dy. So this is just the differentiable. Remark, just don't pay much attention on the existence of differential. That's not part of our course. Okay, so let's look at example A. So we have z or x, y, or f(x,y) like that. X squared plus 3xy minus y squared. And when we know dz is zx dx plus zy, so zx is 2x plus 3y, zy is 3x. Oh, sorry. No, sorry, I'm right. Okay, minus 2y. So dz is 2x plus 3y dx plus 3x minus dy. So this is the differential. Okay. Okay. And then, like what we said, let's look at B. So as x changes from 2 to 2.5, as y changes from 3 to 292, right? Let's compare dz and delta z. Okay, let's first tell you this is delta z, right? This is f 2.5 292 minus f 23, right? What's dz? dz is f x at a point 23 dx plus f y 23 dy. dx is 2.5 minus 2. dy is 2.9 minus 3. This notation, maybe you say, okay, why I introduce so many notation? If you think I introduced too much, the reason that you forget what you studied in Calc 1 or Calc 2. All these notation are just studied before, just reuse it again. If you forget it, you may think I tell you too much information here. Actually, only one, the differential and how to compute it will be. So let's compute the delta Z. So if you plug in this number, so I cannot do it by my hand because the number is big. You use a calculator. You use a calculator. Okay, this one, the answer is 0.6449. Okay, for the DZ, I can compute it. That's why we use this one, because this is, you know, you can handle it. So we can fx23, you plug in that. Let me first compute the fx23, right? You plug in this right here. 2.2.2.2.9.13, right? fy23, you plug it into this, you get a 0. Zero or not 0? No. 0, I think it's 0. So dz is 13, multiply dx, dx is 0.5 plus 0, multiply dy. You don't have to care about the number because there is 0. The final number is this one. So you can say, if you use dz, this is this one, and this is this one. You may say, what are you doing? Why do you tell about this? Right? So we can say the dz is fx, right? A, B, remark, right? dx plus fy, A, B, dy, right? Before we introduce this, we use the delta. Right? I say the limit case is this. In general, we have fxy minus fab is fx, this ab x minus a plus fy y minus b y minus b. This dx is just delta x. This is delta x. dy is delta y. This is delta y. Oh, it's kind of dy is a linear approximation of this part, but this is the actual one. It means that if you use this is kind of the area, the error, right? Because this is this minus this. This is the actual error. This is the error you from the differential. From this problem, you know, okay, they are not far away from each other, close. So means that in the future, you can use this delta z, the differential, to say how big is the error. That's the process. Okay. From this, you can say dz is close to delta x, where this means that fx is approximate fxy. Right. There's the same thing. Now, finally, all the example just to give you some feeling. Okay, the linear approximation is close to the actual, the actual value. Okay, I think this is about the tangent plane and the linear approximation. I think that you focus more on the tangent plane, just to know the differential and try to compute the differential. But the linear, for example, if you study economy, of course, if you study CSE, I think one of you, anyway, well, now we only have 4 students. 2 are from the economy, and, I think some of you are non-degree. If you, anyway, in your field, you may use a lot of material about the linear approximation. That's very important. One thing I want to emphasize is that in our class, we didn't talk about examples related to the applied problems, kind of the margin, some stuff. For example, if you study economy, you just go to the textbook, do that examples for yourself, for your field study in the future, because we don't have enough time to study the applied problem. Okay. I bet if you study economy, you will use many examples in this textbook. Okay, so let me stop recording and continue. Oh, sorry, made a mistake.